So much. It's a great pleasure to speak here. And because this talk and the following one really just have the goal to spark discussion and kind of set a foundation, I decided to really not to go into too much technical details, but give an overview of, without any kind of claim of completeness, of specific insights and perspectives on the overarching topic of entanglement in space-time. And so the first concept that I just want to introduce to you is the page curve and the related volume law that is really at the boundary of black hole physics, but also quantum information theory and even condensed matter theory. So to illustrate the concept, I will show you a very simple setting. So we look at 6 qubits, indicated here, split into 2 parts with 3 qubits each. We have the corresponding Hilbert spaces. The total Hilbert space is a tensor product, and with their respective dimension. And we can think of the set of all pure states as this hypersphere in Hilbert space that we are hopefully quite familiar. And we can now choose a random pure state psi and compute its entanglement entropy, meaning we first trace over all the degrees of freedom in the subsystem B in the complement, here in like bluish, and then compute the von Neumann entropy of this generally mixed state. And that is, as I believe many of you are aware, a measure of how much quantum correlations, so something that cannot be explained by classical statistics, we have in this given state with respect to the system decomposition into A and B. And we can repeat this for another state and just draw the corresponding value of the entanglement entropy in this histogram. We can draw 100 more samples and start to get a distribution. And in the limit, we can really take a random sample of all pure states in Hilbert space with respect to the natural measure on this hypersphere, the so-called H measure that is induced by the action of the unitary group. And for this distribution, which is not exactly Gaussian, but still we can compute the variance and the average. And in particular, if we take the limit of the system to infinity, so thermodynamic limit, more and more qubits, we can ask what is the ratio of the standard deviation divided by the average. And if this goes to 0, we call this average to be typical, because really the vast majority of quantum states have an entropy that is reasonably close to this average, thus being typical. Now we can also plot this average with respect to the size of the subsystem. So here we have 6 sites and would get the value for 3 sites in our decomposition. So that's the subsystem volume VA. We can repeat it for a split 2 versus 4. We can also do all the other values, and we get a symmetric curve because we know that the entanglement entropy is symmetric when we exchange subsystem and its complement, because it really measures the correlations between the two. And so now we can take the thermodynamic limit, look at 12 qubits, 24, 48, and this curve approaches a triangular shape that agrees with this dashed line indicating the theoretical maximum of the most entanglement entropy that any state in Hilbert space can have. So this is the insight that Don Page showed in his paper from '93, that for large quantum systems, the randomly drawn state is very close to maximally entangled. And he studied that in the context of studying the correlations between radiation and a black hole during the evaporation process. But of course, as a question that is completely generic to study quantum systems. Now, we can also indicate in this diagram how the von Neumann entropy looks like when we reduced a thermal state. And in general, at finite temperature, we still expect a linear onset, but with a smaller slope unless we have infinite temperature. So the page curve, this triangular shape, is really the infinite temperature behavior of a quantum system, equivalently a completely randomly drawn pure state. Now, this is in stark contrast to what we expect from ground states of local Hamiltonians that are known, for example, in a condensed matter system, to satisfy an area law. And in this picture, where I really take the volume to be very large, area law states would be really down here. I just mentioned that if you look at this for finite systems, of course, this curve would be round-shaped and just much smaller than the volume triangle. Just to mention that because you will see that in the following talk. Now, how is that related to entanglement in space-time? Well, as already mentioned, Don Page asked this question to study black hole evaporation. But you can also ask in general, if you have a theory of quantum gravity, what type of quantum correlations do you expect in a region of space-time with its complement? And here it's not just a quantum field living on a background space-time, but really also computing the entanglement associated to the underlying gravitational degrees of freedom treated as a quantum theory. But in this case, we expect in general that it is not sufficient to just draw all random states in Hilbert space, because we expect that gravity is a gauge symmetry, and so we should implement these constraints, the gauge constraints. And so a next step, departing from just the page picture where we really average over all states in Hilbert space, is to implement such a constraint averaging over only over quantum states satisfying a certain symmetry constraint. And we did that over the last few years in the context of an abelian U1 symmetry, most recently in 23 for a completely generic U1 gauge symmetry, equivalent to essentially having fixed particle number density, where we still find this volume law proportional to VA, where the coefficient in front at leading order has a corresponding dependence on the particle density that can be computed in closed form from a saddle point approximation. And I believe Yale Yauk is actually presenting a poster on that topic that is included in the booklet. As a next step, going to non-abelian symmetries, as the simplest model that is also relevant when studying quantum polyhedra, for example, in loop quantum gravity and quantum geometries, is SU2, for which we also more recently determined the leading order and also some sub-leading order terms in a symmetry sector of fixed total spin. Now, I should make two comments. The first is, when I speak here about volume, I really refer to the logarithm of the dimension of the Hilbert space in the subsystem A. And in particular, in the context of black hole evaporation and entanglement of a region in space-time like a black hole, we don't expect that the fundamental quantum degrees of freedom scale like the volume of the region, but rather as the area. And that is exactly what also Don Page did when he studied this question in '93. So in this case, it is very well possible that VA is actually not a physical volume, but an area. And the second part, in particular, in the context of SU2, is that there are different ways to compute the entropy, and in particular, one can restrict to just computing the entropy of gauge invariant observables rather than all observables essentially all operators on Hilbert space. And that was done last year in this work here, but it does not change the leading order behavior. And I think you'll get some more detailed perspective on this subtlety in the next talk. Okay. Having introduced this concept of the page curve, let me make a comment on the architecture of space-time perspective through entanglement properties of states. And here I'm referring to a conjecture by Eugenio Bianchi and Rob Myers from 2012, saying that the idea of black hole entropy via the Bekenstein-Hawking entropy formula, saying that the entropy of a black hole is proportional to the area in Planck units with a factor of 1/4, should actually hold in general for a theory of quantum gravity when considering semi-classical states. And semi-classical states refer here to two aspects. First, they should be those states in a theory of quantum gravity that approximate the state of a smooth geometry, and therefore you can actually only talk about regions, areas, and so on. But just having a state that is peaked on a classical geometry is not enough, because if we want to go semi-classical, we do expect that we also recover the type of quantum correlations that you would find, for example, from perturbative quantum gravity, taking a specific background and then treating perturbations of the metric as a quantum field. And in that case, it's very well known that the entanglement entropy should be related to the area of a region. However, the constant is not set because the entropy is actually divergent, as I will discuss a bit more detail in a moment. So this conjecture is really a statement about identifying the types of states in a theory of quantum gravity that both recover classically smooth geometry and gets the quantum correlations on top of this geometry right. And this is quite a strong constraint if you look at it from the perspective of condensed matter systems. We know that a generic state in many-body Hilbert space satisfies a volume law, really here with the volume, similar to the page curve as indicated before. And it's only a small corner of ground states of local physical Hamiltonians and low-excited states that satisfy an area law, often indicated by the kind of physical corner of Hilbert space. That, for example, is very important in condensed matter physics, as those are the states that can be well approximated by with tensor, essentially tensor product methods. Now, most of what we know about entanglement entropy in space-time doesn't come from a given theory of quantum gravity, but rather from probes in quantum field theory, because that's where we can kind of study quantum degrees of freedom in a background geometry, either Minkowski space or, to a large part, really free fields on a dynamical background space-time, so as it is, for example, studied in relativistic quantum information. And in that context, it is very important to understand that the Hilbert space of a quantum field theory in space-time is very different from a condensed matter system, for example, on a fixed lattice, as in particular indicated by the Rie-Schlieder theorem. And in the words of Reinhard Werner, by acting on the vacuum with suitable operations in a terrestrial laboratory here on Earth, an experimenter could, in principle, create a Taj Mahal on or behind the moon. And of course, what this kind of drastic picture refers to is that if you're allowed to apply field operators with elements of a local algebra of field operators in spacetime, for example, restricted to a cushy surface, a region of a cushy surface on Earth, you can actually approximate any state in the quantum field theory arbitrarily well by acting with these operators. So the ground state and also excited states in a quantum field theory are highly entangled, and they do not kind of reproduce the behavior of like a standard tensor product. And that leads to the fact that if you try to compute the entanglement entropy associated to a region in space-time, here on a cushy slice indicated by A, the entanglement entropy will diverge because the Hilbert space does not satisfy such a tensor product structure. And so you would need to kind of regularize it. For example, putting it on a lattice or putting a UV regulator in that essentially allows you to approximate such a tensor product structure. But there is an alternative to look at this, and that is rather than trying to compute the entanglement entropy between a region and its complement, you can specifically define what observables in that region A you want to access, and then compute the entropy only related to the measurements of these observables. And you can construct these by using smearing functions Q and P and define these observables X and pi. And for a finite number of them, and these will be local observables in the region A, you actually will generally find a finite value of the entanglement entropy. But then you can take a step further and build an infinite tower of these observables by using smearing functions Q and P with higher and higher oscillations that probe smaller and smaller scales. And in that way, you will actually recover the area law and a divergence of the entanglement entropy, but now in a physical, meaningful way, because now there's no like ad hoc regulator, but it really diverges as you probe more and more degrees of freedom with your tower of observables. And that was shown by Bianchi and Satz in 2019. Now, of course, this perspective so far was on semi-classical scenarios where we have a background space-time. We can take a step further and ask what happens or what can we learn about entanglement in space-time if we go beyond a fixed semi-classical geometry. And the simple but still stark deviation from a standard semi-classical space-time is to look at a superposition. And what we did in this work from this year, based on previous work by Martin Martinez and collaborators, and also Fu, Magdalena Zisch, Rob Mann, is to look at a superposition of compactified Minkowski spacetimes. Yeah? So we take this superposition where we compactify the z direction in Minkowski space. That makes it relatively simple to treat because locally it's just Minkowski space and it's just the compactification length that makes the different space-time geometries non-trivial. And in this setting, we asked the question of how is entanglement harvesting affected when treating the background not as a single geometry, but as such a superposition. So we have two Unruh de Witt detectors, so just two-level systems that are stationary in one frame with distance a, and that couples for a certain time with a Gaussian smearing with the background field. But this quantum field lives on a superposition of these two spacetimes. And what we were able to show and understand is exactly how the entanglement between these two detectors are affected by the superposition parameter theta. So this is the picture in the middle. It's not a very strong effect for the values that we chose here, but you clearly see a dependence here on the quantum correlations in the middle picture. And I should say here, because the two detectors are, will be in mixed states inside the larger system, we use the concurrence to describe the amount of quantum correlations. Entanglement entropy only works for pure states. And I should just mention that in a similar spirit, this work of Richard Howell, Ali Hackl, and collaborators studied the effect also of superpositions of spacetime, in this case of black holes of different masses, and their effect as a communication resource. So superpositions provides, superposition of spacetime provides one simple way to study the effect of entanglement going beyond semi-classical spacetimes. Now, the last example that I want to discuss is a relationship going back to the page curve and the original motivation from the beginning of studying Hawking radiation and its relationship to thermalization of isolated quantum systems. So if we look at an evaporating black hole, we have this nice picture of the geometry as a Penrose diagram that, very roughly speaking, can be thought of as gluing together, here indicated by red, different pieces of stationary black hole solution. So here we have Schwarzschild geometry as at a fixed mass mi, and we can essentially take a piece of fixed mass and glue those together, of course with a decreasing mass, to describe the idea of classical space-time with proper black hole evaporation where this mass shrinks. And in Stephen Hawking's work that described black hole radiation, he essentially found that on Scri+, and all of this calculation is actually done on the left here for stationary black hole, locally on Scri+, so at plus infinity, the quantum state of the field, here indicated by rho I, looks approximately thermal at a given temperature. Yeah? So if we trace over all the other degrees of freedom, we get a thermal state. And the question of the black hole information paradox is there a way to restore unitarity? For example, how is that compatible with unitary evolution? And I cannot offer a solution to this question, but what we ask is, if there exists a solution that describes the final state of the field as a pure state psi, if we assume that, isn't that very much along the same lines as the thermalization of isolated quantum systems? So that's in condensed matter. We have a globally pure state whose properties locally look like a thermal state, like a mixed state at a given temperature. And you can ask in general, given a globally pure state and the constraints locally in these subsystems to be mixed states, how many pure states are compatible? Yeah? So that's also related to the so-called quantum marginal problem. I know what the state looks locally, how many global states are compatible with that, in particular pure ones. And what we were able to do in this work last year is to construct explicitly a random matrix ensemble describing all pure Gaussian states of a quantum field on Scri+, which locally, mode by mode, perfectly mimics the properties of Hawking radiation. And then having this ensemble, we can of course ask questions like how much correlations do you need, mode by mode, on Scri plus to recover this unitarity or pureness of the global state. And maybe not as a big surprise, but that was essentially the first step of this research program or question. We were able to show that it's extremely unlikely for two modes to be required to be entangled. So here you see essentially a visualization of the space of two-mode correlations, and only in this green corner here, or this very, very tiny green corner here, you have entanglement, proper entanglement, and then we indicate a probability distribution from this ensemble that is peaked either here very much at 0 or peaked over here very far away from the wedge where we have entanglement. And so the probability of a solar mass black hole, that's essentially the calculation here in the middle, is very far from having actual entanglement. And it shouldn't be that surprising because we really expect that it's not mode by mode entanglement, but really more distributed phenomena. And with that, let me just kind of remind you these 5 perspectives on the overarching view and title of this session, Entanglement in Spacetime, Page curve volume law, architecture of spacetime and area law, probing entanglement in quantum fields, going beyond semi-classicality and quantum superpositions of spacetime, and finally, the relationship between black hole evaporation and thermalization of isolated quantum systems. So thank you.
Thank you, Lucas.
Sorry, yes.